Hey everybody, welcome to ARE Live. I'm Mark Tier, the founder and CEO of Black Spectacles. During our webinar today, we're going to review some of the most important concepts of project planning and design, PPD, and share some practice exam questions as we review a mock exam with Mike Newman. For those of you who are new to joining us here at ARE Live, Black Spectacles is the first ever NCARB approved online test prep provider for all 6 of the ARE 5.0 divisions. We offer comprehensive test prep for the ARE with video lectures, practice exams, flashcards, and virtual workshops. And it's all available online with memberships available for either individual architects, firms, or AIA chapters and schools. So if you want to learn more, you can go to blackspectacles.com and click ARE Prep to find more on our ARE study materials. As a reminder, we've launched our ARE Guarantee. We're so confident that if you use our expert membership to the fullest, you will pass the ARE. And if you don't, we're putting our money where our mouth is and paying for your retake. So to learn more about how to qualify for the guarantee, go to blackspectacles.com and then ARE Prep, and you'll find all the details on our ARE Guarantee. As I mentioned, we have group memberships as well. So to learn more about how you can have your whole firm on a membership and have your boss pay for it, go to blackspectacles.com and head to our pricing section. Our next ARE live broadcast will be on November 11th of 2021, and Mike Newman will return to review some of our most important concepts of project management with a mock exam. Today, we're going to be engaging exclusively on our online ARE community. So head over to that thread if you haven't already. I'm going to go there right now. So if you go to blackspectacles.com and if you go to resources, you'll find the link to ARE community. And then when you land on the homepage for the ARE community, you'll see a button toward the top that says ARE Live, and it's the first thread there. So check that out. Everyone who posts in that thread today will be eligible to win a free Black Spectacles t-shirt. So head over to community.blackspectacles.com and say hello. You don't even have to write a fancy question if you don't have one. All you have to do is say hello, and that will make you eligible to win a free t-shirt. And don't forget, we'll announce the winner of that free t-shirt at the end of the podcast. So make sure you stick around to see if you won, and so forth. So the last thing to share with you is that today we have a special discount on all Black Spectacles ARE Prep memberships to share and help you along your journey. So I'll provide that coupon code at the end of the show. So stick around for that. Our guest today is Mike Newman. He is the founder of Shed Studio, and he is a accomplished professor at a number of the schools of architecture here in the Chicagoland area. He's also our instructor for our Black Spectacles ARE Prep video lectures. And so with that, I'll hand it off to you, Mike.
Okay. Good to hear from you, Mark, and looking forward to this one today. I think probably the smart thing here is just to dive right in. One quick reminder that the way that the exams are set up, as I'm sure all of you know, is you have the sort of the 2 management exams that are sort of a separate kind of category. And then you have the 4 exams in a row, one that starts with kind of initial issues and analysis, then getting into planning, which is this one, planning and design, and then into planning and design and documentation, which is the next one. And then the 4th of that series is the one that is sort of when the architect is kind of helping the construction process go along through the construction administration end of things. And so it's kind of a timeline through a project, if you will. And if you think of it that way, it allows you to see the questions a little differently. You could get almost literally the same question on multiple exams. It's just that the agenda would be different because it'd be at a different point along the process. But let's just sort of jump in here. Let's see if I can get, oh, there we go. And we're just going to run through a couple of questions that kind of get to some of these kinds of issues and the sort of way that you are thinking about how to approach projects in the sort of early stages of the design thinking. So this first one, question 1, the concept of continuous insulation has become a common requirement in building codes across the country. What is the main reason for this? And we have a couple different possible answers. reduces the thickness of the walls, reduces thermal bridging, more cost effective than regular insulation, creates a better acoustic separation. So let's just think about what this can mean generally. So I'm going to just do a quick sketch here. So imagine I'm sketching a portion of a wood framed wall.
Need to get you some sketching music, Mike.
Yeah, that would be good. Like Benny Hill or something.
That's fine.
So I've got sill plate and I've got, or sole plate, I guess, actually, and I've got a couple of studs coming up, and you can imagine this is a continuous wall, and those studs are at 16 inches on center, 24 inches on center. I've got some sheathing on the outside, and in between these studs, I've got a bunch of insulation. So I've got insulation in between the studs as we, the wall is sort of filled with that. There's a bunch of other things in there too, there's electricity and all that kind of stuff. But essentially, I've got all that going. And then on the inside, obviously, I have drywall. So I've got a drywall face across that whole thing. And for most of the recent history, that's how we built small buildings. Might be with metal studs, might be some other things, but essentially we did something like that. We had those wood studs set apart from each other, and then we fill the cavity space with insulation. And that's great. The thing about insulation, right, is that it's kind of an interesting material. If you think about how materials conduct heat energy, effectively all materials conduct heat energy. Just some conduct it very, very well, and some conduct it very badly. And so an example of something that conducts it very badly, we would call insulation. So we like the fact that it conducts heat energy badly. That means it slows the process of the heat energy moving through our building envelope. So just as a quick kind of way to picture that, if you imagine yourself standing outside on a freezing cold day, and say there's three objects in front of you, and one is an aluminum bar, another one is a piece of a 2x4, a piece of wood, and a third one is a chunk of styrofoam. If I pick up the aluminum bar on that freezing cold day outside in the winter, and I'm holding it with my bare hand, that bar is going to feel really, really cold. And the reason it's going to feel really cold is because the aluminum is very, very good at conducting heat energy. And so it's going to conduct through conduction heat energy right out of my hand and into the aluminum, and it's going to feel incredibly cold. I can then put that down and pick up the piece of wood 2x4 and hold that, and it will feel quite cold, but not as cold because it's not as good a conductor. So the wood is, it will conduct the heat energy, but it's not as good a conductor as that aluminum was. And then I could put that down and pick up the piece of styrofoam, and it wouldn't really feel all that cold at all. Because it's a terrible conductor at heat energy, which is why we like it for coffee cups and insulation and things like that. Now, styrofoam also has lots of sustainability issues in terms of toxic chemicals when they're making it and things like that. But push that to the side. We have these three materials. One feels absolutely freezing cold. The other one feels cold. The third one, it's not, you barely even notice it. But interestingly, they're all outside on that freezing cold day. So they're all actually the same temperature. It's just how it feels to us because of their ability to conduct heat energy. So the insulation in the walls like this are the reason that insulation is good is that it's just poor at conducting that heat energy. Well, the wood studs are, remember, in that middle zone. They're not fabulous at conducting heat energy, not like that aluminum bar, but they're still pretty good at it. They're good enough at it that what that means is that's a good place for heat energy to travel. So if you imagine that, you've got inside nice warm air inside on a on a cold winter day, and that heat energy from there is going to want to travel through the wall. Nature always wants to balance itself, so the higher heat always wants to find the lower heat in order to kind of find a happy medium. So it's finding its way through the wall every chance it can in order to balance that out. Well, as it tries to go through the portion of the wall that has all the insulation, it's going to have a hard time getting through because the insulation is a poor conductor of heat energy. But the wood is not a bad conductor, and so it's going to find its way right on through. And so that wood in that stud is going to act as a thermal bridge that is bridging from the inside to the outside, creating a pathway for the heat energy to get lost from inside to the outside. Now, I'm using the winter as the example because it's sort of obvious, but we could be having the same conversation about the summer. It's just that the heat energy is flowing from the outside to the inside, meaning that we now have to air condition more in order to get rid of that heat energy that's come in. Now, all insulation will eventually, heat will still find its way through, but you can see that there's really a difference between these different aspects of the heat energy loss from these different materials. So this was the sort of way that we built for decades and decades. You still find it in a lot of situations. But these days, what's sort of being asked for is starting to add another layer on the outside, and then maybe a finish of a rain screen or some other finish material on that. But that layer becomes an insulating layer. And notice that it goes right across all of those studs, those vertical wood members. So there is no place now in that wall where I have this straight thermal bridge from inside to outside. I still have a better and worse part of the wall, the part that has the original insulation, and then also this added insulation, this continuous insulation, is going to clearly be better than where the studs are. But where the studs are still going to be pretty good because I have this insulation going by and I don't have that immediate thermal bridge capacity to just lose heat energy out. So these days, the codes in much of the country are now requiring the idea of continuous insulation in various situations. I will say that when I remember back years ago, early in my career, and it's like maybe 1995 or something, and I drew something like this in a wall section, and I was showing it to the contractors, and the contractors were like, just like, forget it. You got to be kidding me. That's just way too much work. We're not going to, that's a whole second layer of the wall. We're not going to do that. Like people just didn't expect to do continuous insulation then. Now, if you show a contractor a wall that doesn't have the continuous insulation, they're like, what's the matter with you? Like, that's crazy. You're going to lose all kinds of heat energy. Like there's been a whole flip in how people expect, how we think about the envelopes of buildings. And the idea of this sort of continuous insulation is really a sort of conceptual idea. It's not related to the wood studs. These could be metal studs. It could be CMU concrete block backup with a brick veneer and that air space in between. I have a run of continuous insulation there. It's an idea of finding ways to make sure that we don't accidentally create ways that we just lose heat energy and therefore are wasting that heat energy. So continuous insulation, the answer here is going to be that it reduces, it reduces thermal bridging. Now, kind of interestingly, it actually, in terms of it actually thickens the wall, doesn't reduce it. Excuse me, to C, more cost effective. Yeah, you could say that, but it doesn't really hold true. It doesn't really make a lot of sense, as it'd be hard to sort of kind of make that a really clear answer. and D, creates a better acoustic separation. It actually does create a better acoustic situation. So that's a correct answer. It's just not the correct answer. There's a better answer, which in this case is the reduces thermal bridging. All right, gonna move on. Okay, question number 2. In a new design for a building in Denver, the design team is considering various options for the fenestration. Fenestration, hopefully everybody knows the term. It's the fancy word for window pattern. So new options, various options for the fenestration of a building. Which side of the building will be the hardest to control solar heat gain? So this is probably one that most of you know, but just in case, we're going to run through it here. So imagine we have our building here. There's north, east, south, west. First thing to sort of think about when we are talking about solar heat gain, especially through windows, is there are times when we like it and there are times when we don't like it. And pretty obviously, in the summertime, I probably don't really want to get a lot of extra solar heat gain. It's just going to increase my air conditioning load. It's going to be problematic because it's going to overpower the building. But in the winter time, getting that extra little bit of solar heat gain is actually going to be a big positive, because what it's going to be doing is reducing the energy I'm going to use in heating the building, because I'm going to be stealing a little bit of that free solar heat coming through the windows. So I like it in the winter and I don't like it in the summer. That's obviously a simplistic way. Most of these questions are going to be, you're going to have to take them in sort of simplistic understandings, because you have to be able to make a decision off of a very little bit of information. Clearly in the summer, there are going to be cool days, and in the winter, there are going to be warmer days. But you can generally say solar heat gain in the winter is good, solar heat gain in the summer, and not so good. You actually want to block it as much as you can. So, all right, we're looking at the plan of this building. And if you imagine in the summertime, the sun is going to be rising about there, roughly, rising up and then setting down about there. I'm fairly rough justice here on this, obviously. And then in the winter time, it's going to be rising there. You can see that I'm below due east. So there's rising, and it's much lower in the sky. And then it's coming back again. So in the summer, it's rising up as it moves along, and then falling down low as it goes to set. In the winter, it's rising up as it moves along, and then falling down low as it goes down to set. So if we look at that building in section, we can imagine in the summertime, if this is the south face right here, in the summertime, that sun is very high in the sky. In the wintertime, that sun is quite low in the sky. So that sun is coming right down on the building in the summertime, and in the wintertime, it's coming in sort of almost sideways at the building. And then obviously in the spring and the fall, it's between those two. So what this means is we look at this building, we can see that the south is really getting a lot of the sun, both winter and summer, and therefore also spring and fall. But I'm going to have a fairly easy time of putting a small little blocking system there, and that's going to bounce that solar heat energy away from the building. But in the winter time, when I actually want it, it's going to go right underneath there. So I am able to control that solar heat gain fairly easily on the south side in a way that's probably a little unexpected, because you might think that the south side, well, it's getting all that sun, it's got to be the hardest place to control. But in fact, because there's such a grand difference between where the sun is in the winter versus where it is in the summer, that it allows me easy way to control when I want to get it and when I want to block it. So let's think about the other sides right now. Well, let's think about the north for a second. Well, I'm getting almost no, very, very little direct solar gain onto the north face at all at the very beginning of the morning and at the very end of the day, only in the summertime. And in the wintertime, it's not even going to ever get any direct sun. So north can't possibly be the right answer. So we're going to X that one out right off the bat. So south seems like a good answer in terms of what's going to be the easiest to control, but let's sort of play it through. What about west? So now let's take a look at this western example. So I'm going to be looking at our building. Now this is the west facade. And remember that the sun is rising from the east in the summer, and it's rising from the east in the winter, and it's setting on the west in the summer, and it's setting on the west in the winter. So in both of those scenarios, east and west, in both time frames, summer and winter, the sun is that low sun angle. So here we are at the low sun angle. I'm kind of making up a sun angle here, but it's coming in down low, but it's never at the high angle on the east and the west because that it's in the process of either rising or setting. So in both scenarios, when I want it and when I don't want it, it's down at that low angle. And so it means that I just don't have this easy way to control, well, okay, in the summer, I'm going to block it in this way, but in the winter, I'll allow it in this other way. Like I can't control the difference. They're both low angles. And so I just don't have that ability in a sort of easy way. Now, there's lots of other things I could do. I could have, shading systems that move. I could, provide, curtain systems or all kinds of other things. But there's not a simple, easy control way for the East or the West. And since the West is the one that I have as a possible choice here, the answer is going to be that A, the West, is going to be the hardest of these three sides to control. Now, interestingly, if there was a D East, I would still say that West was the hardest one to control, even though they're essentially the same. And the reason for that is that if I'm worried about solar heat gain, I'm going to be less worried about it in the morning because the morning, the day hasn't warmed up yet. So I just don't have the same concerns that I would have at the end of the day after the whole building has gained all that solar heat from the big bright sun and the earth is all hot and everybody's, the whole day is just is become hotter and hotter all day. And now that sun is setting and now I have that low angle sun coming right in my west facing glass. So I would say that the West was still the worst in terms of controlling in comparison between the East and the West, which would be a little hard, like, technically they're exactly the same. It's just that it would feel different in the afternoon because there would already be so much solar heat gain. So it's a little funny what we're talking about here. What we're saying is that it's about, are there easy ways architecturally to sort of answer this issue? And the big question when it comes to solar heat gain is just that simple understanding that I want it in the winter and I don't want it in the summer. All right.
Hey, Mike, real quick question from
Yeah.
our ARE community. I don't know how to say their name because it's probably their last name, Wailuka, I think, asked, wouldn't the answer be West no matter if the building is in Denver or not?
Yes. Yeah.
Well, that was easy.
Yeah, there you go. The idea was just putting it, so it was in a place that was kind of in the middle of the country that, so it was you could kind of picture the east, west, and north, all of that. It does get a little more complex, but you wouldn't get this kind of question on the exam because it starts getting nuanced. and
Right.
they don't want nuance on the exam. They want fairly
Right.
clean, simple understanding. But clearly there's a difference in sun angles if you're in, say, New Orleans versus if you're in, say, Anchorage, Alaska. So it's actually quite a different conversation when you start getting that far north, because even the high angle of that summer sun is actually not as high as you would have it in the main body of the United States, the 48 contiguous states. So it could actually be a slightly different conversation. So we're just kind of nailing it into the kind of middle of the country. So exactly, it holds true for this conversation. But it would be very similar in Chicago or Minneapolis or San Francisco, or anywhere in the sort of middle range, and would be still true even in the extremes. It's just that it gets a little more complex.
Perfect. Thanks, Mike.
Great question. All right, this is another one of these kind of simplistic ones, just trying to sort of get you to think at a sort of base level. So the question is, question 3, which of the following building floor plan shapes would be best for a cold climate like Buffalo, New York? Again, Buffalo, New York, nobody cares about it. That's not the key here. The key here is cold climate. And so when we're talking about cold, it's not giving us any other information. So we're not talking about fenestration or solar heat gain or anything like that. We're just talking about the fact that it's cold. And given that, the big issue we have, the big thing that we're thinking about is heat loss. So where do I lose heat? Well, I lose it through the perimeter of the building. Now, I also lose it through a couple of other things, like when people open doors or open windows and some things like that. But those are sort of incidental. Those are about use. You can't really control that in this kind of a question. So what we're talking about here is I have an envelope, a wall system, and a roof system, and that envelope is losing heat energy out through it, out from the nice warm space inside that has a heating system to the cold exterior. So our basic issue here is what's going to create a better situation in that scenario. Is it going to be to have more wall area and more roof area, or is it going to be to have less wall area and less roof area? And it should be sort of obvious once I say it out loud like that, that yeah, clearly the whole point here would be to have the least wall area compared to the amount of floor area that I have, and the least roof area compared to the amount of floor area I have is sort of total envelope. And the way that I'm going to do that is by going with the nice, simple square system. So if you kind of calculate it out, you can do a quick set of calculations in your head, and you can realize that actually a circle would be even more technically efficient. But the square is going to give us the most square footage for the least perimeter envelope. If I have the long, thin rectangle, I'm going to have more wall area than compared to for the same floor area compared to the square. If I have the courtyard, I have certain advantages with the courtyard, but a bunch of disadvantages, and the obvious disadvantages, I now have even more wall area that I can lose heat energy through. The L shape is going to be similar. I just adding wall area compared to the floor area. So it's just a simple discussion of what's the issue in that cold climate without any other information. And the only thing we can really think about here is heat loss through our envelope, and the square is going to be the most efficient of them. Now, having said that, there's all kinds of reasons why you might not want to build a square. That's not really the point. Like once you look at a site or the context, or understand maybe you can use the fenestration and get some really useful solar heat gain at certain times of the season and kind of change things around. There's all kinds of reasons why you might use a different shape. But in this context, in this question, all we know is the heat loss issue of the cold climate. And so you're going to go with the most efficient, straightforward system. If we were being a little more complex and we had more information about fenestration or something, I might actually choose not as long a rectangle as that one, but something of a rectangle with windows and then a shading system on it, just slightly oriented south and a little bit towards the east. That would probably be, once you start getting into fenestration and solar heat gain and all of that, that would probably be like the perfect mix of reducing the exterior wall surface, but adding in as much wintertime solar heat gain as you could. So if you had more information, you might be able to make a more nuanced conversation, but this is very simple, one line, and it's just asking you what's going to be the most efficient, and in this case, it's going to be the square. Okay, number 4, question 4. The architectural team has finished a schematic design for a 6-story office building for a new construction project in Cleveland. Most of the building is clad in glass, a glass curtain wall system. The window wall ratio, WWR, as designed, is approximately 75%. Due to this WWR, what will be required? A, with that much glass, hydronic or electric radiant heaters will be required at the base of the windows to reduce condensation buildup. B, according to the IBC codes, the structure must be a concrete frame for stiffness to reduce potential for building movement and thus cracking of the window systems, glass, or sealants. C, according to the IBC code energy requirements, the building will not be able to be designed through the prescriptive method, and instead an energy model will likely be required. D, to reduce the solar heat gain from the large amount of glass area, exterior shading devices will be required. So if you kind of think of the window wall ratio, like imagine you're doing this building, and we'll do a little tiny version of it here. I've got a little curtain wall. I didn't quite get enough floors there, but I think it'll do. And so I've got a little bit of solid, it's maybe glass material, but it's a little bit of spandrel. So it has the ability to be insulated, but it's essentially mostly glass. Now, 75% would be pretty high percentage, but you could imagine you could have essentially all glass facades, and that would have, there'd be certain interesting things that both design and for sustainability reasons, there may be some advantages, but there's also a bunch of disadvantages. The obvious disadvantage of having a lot of glass is that glass is a terrible, terrible, terrible insulator. Now, the glass today that you can buy is way better than what you could buy, say, 20 years ago. And it's, maybe double or even triple the insulating capacity, which is fantastic. That's great, but that's still terrible compared to an insulated wall. So, having a lot of glass is going to be super problematic. Because I'm going to have a lot of place where I'm just really badly insulated for this building. Now, interestingly though, it's not that that's the only issue. The other side of that is, well, with the glass, I also get a lot of nice, fresh, free daylight that I don't have to have my lights on inside as much because I have a lot of light coming in from the outside. And so I'm saving energy potentially on my lighting bills. I'm also getting, as we talked about, that solar heat gain at certain sides of the building at certain times of the year. So there's certain advantages to having a reasonable amount of glass, but there's also, as we said, a bunch of disadvantages because it's just such a bad insulator. So what that gives us, if we start comparing that little building that, say, is at 75%, well, another building, same situation, maybe this one has punched windows. And I'm not going to draw a whole lot of these because it just takes too long. but you get the idea. A bunch of punched windows. Well, clearly I've got way more solid wall and therefore well insulated wall, et cetera, et cetera. So, you know, I can have roughly the same building inside with very different window wall ratios. And what this is all kind of getting to is that the ASHRAE folks and the IBC, International Building Code, and various other folks have kind of gone through the numbers and have sort of realized that there's kind of a happy medium. I want to have enough windows that I get all of that free daylight. I want to have enough windows that I'm getting some beautiful solar heat gain in those winter months when I really want it. But I don't want to have so much window that any heat energy or any cooling that I put into my building, I'm essentially just losing out through all of these poorly insulated glass walls. Now, like I said, they're way better insulated than they used to be, but they're still comparatively really terrible insulators. So they've kind of gone through, crunched those numbers, and there's sort of a reasonable range that they've found that you can be pretty sure you're going to be getting all the benefits, but not having a full building of losing all that heat energy. And depending on the climate, depending on the construction type and a few other issues, it might be that it's, say, somewhere between 35 or 45%. So I might have a window wall ratio of 40% or 45% or 35%. And that's giving me enough window, kind of like this example here. It's giving me enough window area that I'm getting all those positives, but I also have a lot of well-insulated wall, so I'm not getting all the negatives, at least not the scale of which I would with this particular example in the question. So there's these dividing lines for different climates and different situations, but they'll all be in that kind of rough range there, where if you're below that window wall ratio, then you can just follow the rules. There's a series of prescriptive rules that you're allowed to just, you know, if you meet that WWR, well, then you can just follow that set of rules. So it might say for a climate that you're working in, that say the typical wall section must be meet an R23, reasonably well insulated wall. And maybe the roof will say it has to be at least an R40 or 45 or something like that. And so it'll just give you these rules, and then you can just say, when you're permitting or whatever, you can say, okay, we meet the requirement of the window wall ratio, and therefore we're going with the prescriptive method. And here's the rules that we need to follow. Here's the R23 at the wall, and here's the R43 in the roof, and so therefore, you know, we're good to go. And nobody really needs to go through and calculate anything. They don't need to spend a bunch of extra time kind of figuring it all out, because this is sort of a happy medium that people over the span of years have taken lots and lots of information in and kind of developed and sort of said, all right, if you follow these rules, we can be pretty sure it'll be a reasonably sustainable building and will work well in that particular climate zone with these particular rules. But we still want to have people be able to design other things or try new innovations. It may be that, yeah, that glass is a terrible insulator, but maybe we're going to do a double glass wall, and we're going to have convective currents running up in between them to kind of help heat and cool or temper the air before it gets used for heating and cooling. Or we're going to find shading systems that are going to allow for different ways of controlling solar heat gain, or we're going to use, you know, some other kind of novel way of approaching this, or we're just going to make a certain percentage of the wall very insulated, and that's going to balance out the lesser insulated glass portion. So there's lots of things that I could do in order to make something with that higher WWR sort of be reasonable, but it's just, I can't do that by just following those simple prescriptive rules. And so there's like this dividing line. And if I'm below on that, I can follow the prescriptive rules, no calculations needed, straightforward, everybody gets it. But if I want to go above that, well, then I'm going to have to prove it. And so I'm going to probably need, not necessarily, there's a couple ways I could do it, but I'm probably going to need an energy model in order to be able to show that we're still meeting the overall heat loss worries that the code requirements would have. So it's kind of an interesting thing. Nobody's trying to stop you from designing what you want. They're just trying to get the buildings to meet certain requirements. And we also want to make it as easy as possible for most buildings that don't have a lot of extra engineering capacity for cost reasons or just what's available. And so there's ways that you can design that meets all of these issues. And at the same time, there's ways that you can go beyond that and do something innovative and new and trying something different. But then you have to be able to express that, yes, in fact, you're meeting all of the heat loss worries that would be built into the code. So the answer here is C, I believe. Let's see, according to prescriptive method. Yeah, so it would be C, that when you see that WWR, that's typically going to be talking about that moment of flipping back and forth between the simple prescriptive methods or the more complex ones where you have to actually figure out through formulas and modeling systems how that's going to work. Now, a couple of other points to make on these. With that much glass, a hydronic or electronic radiant heaters will be required at the base of the windows to reduce condensation buildup. In Cleveland, that's probably not a bad idea. That, you know, in the winter in Cleveland, you're going to get pretty cold outside, and you're going to have a nice warm inside space with lots of people breathing and sweating and you know, making coffee and some steam going into the air and all of that. So there's a lot of moisture buildup in that air. That moisture is going to be nice and warm air and moist warm air. And then as that warm moist air goes over towards those cold windows, the air is going to cool down. And what do we know about air? Well, warmer air can hold a lot more moisture than cooler air can. So that same body of air, that same cubic foot of air, if you will, that moves from the interior and gets very moist, moves over to the exterior, gets very cold next to that cold window, and it's going to start dropping, leaving behind its some of the moisture, because it's going to get to the point that it can't hold all of that moisture, and so you're going to get condensation on the windows. So that's not a bad idea, putting those radiators below, because that will warm up right below the window. You'll get a sort of warm flow of air rising up across the window. It's going to pick up all of that condensation. It's going to create a buffer between the cold radiant source of the cold window and the bodies, the people who are inside. So it's not a bad idea. And in a place like Minneapolis or Cleveland or Chicago or Boston or you know, cities like that where it gets reasonably cold, you know, you're going to find that quite often, but it's not really about the window wall ratio. It's just not, that's not the issue. It's just probably a good design practice, depending on what other choices you're making. And then if we look at B, the structure must be of concrete frame for stiffness to reduce potential for building movement. You know, there may be reasons why you would want a nice stiff building, but again, it doesn't really have anything to do with the window wall ratio. The curtain walls are set up in order to be able to have a little bit of movement within them, at least they should be. So it's just not related. There may be reasons to want a stiff building, but it's not related to the issues of this question. And then D, to reduce solar heat gain from the large amount of glass area, exterior shading devices will be required. Again, kind of like the hydronic or electric radiators at the base of the windows, probably a good idea. It just doesn't necessarily have anything to do with the window wall ratio. So lots of potential correct answers, but there's just one that's the actual full correct response.
Thank you, Mike. Before we hop into question 5, one of the questions we got in the community, which actually isn't specific to this particular question necessarily, is a broader question from Delis3, said, can we save a couple minutes to discuss a difference between the PPD exam and the PDD exam? Mike, do you have any comments
Yeah.
on the difference between those two different types of exams?
Yeah. So the planning and design, if you know the sort of classic scenario, they very consciously didn't use the normal way that we would talk about these things, which is schematic design, design development, and then CDs for contract documents, bidding, and then CA, construction administration. And they didn't want to tie it to those terms for, I think, good reason. But effectively, the analysis one, the one before this, is really like, okay, imagine a client has come to you and they say, you know, we want to build a project, you know, so the survey, you know, getting to know the land, doing research about what's the climate like, does it rain a lot, how cold does it get, where is the sun compared to the site, do we have contextual issues, big picture design issues like, is the soil good enough that we can have a reasonable foundation, or are we going to have to put caissons 1,000,000 miles down in order to get to bedrock, right? So kind of big picture, where is it on the site? What's the context like? Things like that. So that's kind of it, sort of pre-design. It's kind of at schematic design and all those kinds of thinking. Well, this exam is, you're talking about kind of planning and getting into design. So you've already done the analysis and the sort of straightforward kind of looking at, you know, how much rainfall is there and things like that. Now you're thinking about the design. So you're doing kind of that schematic into design development range. So you're starting to draw the elevations. You're looking at, you know, things like the window wall ratio, because you're trying to get a handle on kind of what does the building actually look like. We've already got sort of, you know, maybe an initial concept, but now we're actually designing it. And so we're figuring out what makes sense and what works. And so we're finalizing things like the building shape, the wall system, the, you know, getting a clear idea of the wall section, getting into the materials. You're sort of moving from that very first kind of design thinking into that kind of design development realm. And then the next one, the PDD one, now you're talking about documentation, right? So now you're moving from design development into the contract documents. So you're creating permit sets and construction drawings and all of those kinds of issues, and starting to get into bidding and that sort of stuff. Bidding will also fall into the last one as well. But so the documentation, that's where you're really getting into, okay, not just like what the WWR is, kind of what this thing looks like, but you're getting into what's the detail, where's the thermal break on the curtain wall, right? You're getting into how much CFM am I putting out into this room in order to keep it warm enough on the, you know, coldest day of the winter. You're getting into that detail level that is, we've moved past now the sort of general design issues of materiality and space and all of that, which shows up on this one, and we've moved into the realm of details and communication of those details to other people. So to code officials, to contractors, to all of those folks. It's always interesting to think about what the term CDs means. People will talk about it as construction drawings, CD. Some people will, you know, use some other ones. Technically, it's actually contract documents. That's what the CD means. And it's interesting to think about why we use that term. We also will say, just, you know, colloquially, we'll use construction drawings or construction documents because, you know, we're trying to be clear about what we're saying. But technically the contract documents is there because your work, right, your set of drawings at the end of when you've done all of that work is actually the contract between two other people. So your work is not a building, your work is the contract to make the building. Now, obviously there's also a written contract and there's a bunch of other stuff involved, but that written contract will say, and drawings by, I'm forgetting the name of the questioner, but drawings by X and dated at this time, and that's now part of that contract. And so you immediately, once you realize that CD means contract, that you start realizing, oh wait, my work at this stage is about being able to communicate for other people. So it has to be a communication. I'm not even in the room. The owner and the GC are the ones in the room. Now, I'm probably also there too, but technically those two people are having a conversation, and their conversation is through my drawings. So the documentation portion of the exam is really about that kind of conversation. So conversations with code officials, details, conversations with GCs, meeting all those final kinds of issues that you would need to meet. On this exam, what we're really talking about is the design, the what the material is. So if you think about what it means to be the difference between schematic design and design development, by the time I get to the end of design development, I should really know what all the materials are, right? It's a brick building with punched windows and then this one curtain wall to emphasize the entry, right? Okay, I can talk about all those materials. I haven't necessarily drawn all the details of all those materials yet. I haven't necessarily gone into sort of a full mode description of every aspect of it, but I should know the spaces. I should know the size of the rooms. I should know the materials that are there, and I should be able to have that conversation to get to that point of knowing those materials and knowing those designs. So this exam is where we're going through that process to get to that point of knowing that information. And then the next exam is going to be, okay, we've got the design, now we're detailing it so we can communicate it, we can document it, and give that information to other people.
Awesome, thanks,
Hopefully
Mike.
that was
Yes,
reasonable.
great. Yep.
Okay, let's finalize this thing here. Question 5. The client has asked for a 4-story building of 40,000 square feet per floor. During a code review, the determination is that the occupancy and the construction type together reveal an allowable floor area of 30,000 square feet per floor. What should the architects do? A, we could explain to the client that the code only allows 30,000 square feet per floor and help find ways to save space on the layout so they can fit. B, we could design a 6-story building to accommodate the client's space needs, because it was going to be a 4-story building at 40,000 square feet per floor. They're saying, all right, we'll make it a smaller per floor, but taller. C, we could initiate the process for code request for variation from the local building department. Or D, we could propose a 4-hour rated building wall or firewall that divides the floor plan into separate buildings. So there's a couple of possible ways that you could answer this, but the simple answer is going to be, well, for one, we can say telling the client not that they can't build what they want. That's probably not going to get you a lot of projects. So we're gonna cancel that one out if we can. But if you imagine your 40,000 square foot floor plan, and I'm just for simplicity's sake going to say, and here's a corridor, and there's stairs and elevators somewhere. The word building is kind of interesting. It has potentially multiple meanings. And in this case, this is clearly a building, right? We imagine it's got exterior walls. We could stand outside and look at it, and it would look like a building. But if I built a big 4-hour wall down the middle of it or somewhere in it, and made sure that this side here was no more than the 30,000. And then this other side was whatever we needed that was left. I'm essentially turning that one building into two buildings that make up one building. And so it's a little weird because they use the same term, but effectively, by putting that firewall in, that building wall, we are dividing the building into two separate buildings. Now, I have this corridor that runs between them, and you've all probably seen this many times where you're walking down a corridor and then there's these weird doors that are open. So I have those doors that, if they were closed, would continue that building wall. But when they're sitting open, I think that's too small for me to draw, but there you go. When they're sitting open, they're being held by little magnets or some device like that, that when the fire alarm goes off, the magnets let go and the doors close, and that wall becomes a continuous 4-hour or 2-hour, depending on the situation, building wall. And so what you've effectively done is you've used the code and sort of figured out how to make the code work for your situation. Now, it's not cheap to build that wall, right? So it may actually be better to do something else, but the code is never telling you, if it says you can only build 30,000 square feet, it's not telling you you can only build 30,000 square feet. What it's telling you is you can only build 30,000 square feet if you are only doing this one thing. I can then do something else and build bigger, or build more, or have a longer distance, or whatever it happens to be. So the issue here is the reason that we wanted to use this question is we want to make sure that you're realizing that the point of reading the codes is not to be sort of told exactly, oh, the table says I can only build, X or Y, or it's to use the code to figure out, all right, how do I do what we need to do in this situation? And in this way, you're realizing that there's this terminology that allows you to think of a single building in a more dynamic way. So if this was, say, the same numbers, but we were trying to do a 90,000 square foot building, well, we could have more than one building wall or firewall, and have this exact same situation. And for the user, nobody even really needs to know. Like, they don't care. They're just walking down the corridor and there's a weird door sitting open, but what do they care? And then in a fire, the door lets go, it closes down, you have a continuous wall. It's still a door, so you can still move through it, but it's a fire-rated door that will stop smoke and heat to some degree for at least a period of time. So this is sort of that example where don't get pushed around by the code, use the code to find ways to do the things that you need to do for your client. Now, you would never want to do something that's unsafe. So you might have a conversation with the client about, yeah, we can put this wall in, but I feel uncomfortable with it because I don't like how the safety is working here. Like, that's a reasonable conversation. But if you feel like it's still safe, and it would be safe because a fire here is very unlikely to get through that wall, so you are in fact increasing the safety of the building by doing this. Nobody wants you to build anything that's unsafe, and you certainly don't want to encourage you to let an owner just sort of push you over to build something that's unsafe. But at the same time, you need to be able to work the codes in order to be able to get the buildings that you need. And that's what's expected. They're written in that way. So when you read them, you'll find that almost every time it tells you no, it actually also tells you how you can do it. It's just that it's going to add other requirements in order to keep the building safe and healthy and functional. So the answer, what was the answer? There it is. D. Okay.
Beautiful. Thank you, Mike. I think we've hit most of the questions that are in our ARE community. So I think with that, I can say thank you. Thank you to you, of course, Mike, and thanks to everybody for tuning in. As I mentioned at the top of the show here, our next ARE live broadcast will be on November 11th of 2021, and we're going to review some of the most important concepts of the project management exam and share some practice exam questions as we do review a mock exam just like today with you, Mike. So that's what's going on next. As I mentioned at the top of the show here, we've launched our ARE guarantee. We're confident that if you use our expert membership to the fullest, you will pass the ARE, and if you don't, we'll pay for your retake. You can learn more about that on our website at blackspectacles.com, and also to learn how to get your whole firm on a membership and have your boss pay for it, go to blackspectacles.com and head to the pricing section and look up firms. The lucky winner of a Black Spectacles t-shirt is Gloria M. Gloria will reach out to you via email today to get your size and shipping information. Thanks to everybody who posted on our ARE community. There's a lot of really good questions over there. And if we haven't already answered them, we will diligently continue working on getting you answers to your questions. The thing I want to mention to everybody is that our ARE community is actually a free resource for anyone at any time. So it's not just for ARE Live. So if you have a question as you're studying, regardless of whether you're using Black Spectacles materials or not, it's a free resource for everybody. We have licensed architects who pay attention to the posts on there, and they work to provide lots of answers and provide a lot of information. So it's a great resource. This month, we're offering a 15% discount off of any of our expert level memberships. So you can use the code ARELIVEOCT15 to get 15% off any of our expert memberships and to gain access to our virtual workshops and the ARE guarantee. So keep in mind the coupon code expires on November 11th of 2021. So you'll want to keep that in mind. But if you're ready to start studying, you can head to blackspectacles.com/pricing/individual to sign up and use that code at checkout. Finally, be sure to stick around for a few minutes to take our survey and share any suggestions that you may have. Suggestions about the format, suggestions about the topic. I promise we really do read every word that you write and use them to tune our next episodes. So thanks for watching.